Hi, hello everybody. We're looking at 8.3 today. The last thing that we did was talking about this basic form for quadratic equations, the y equals ax squared plus bx plus c. And last time, I think we only focused on this part of it, just looking really at the number that comes before the x squared term and what it does. This time we're going to add on this piece, the little plus c at the end. So plus another number, minus another number, and what that does to the graph. Right, so let's jump right into it. Our first example gives us x squared minus 2. So if you recall, x squared is kind of like our base point, our parent function. And it's a quadratic equation that has a point right here at 0, 0, and it goes up to the right, up to the left. So what we're going to do is compare how this function looks different than y equals x squared. So minus 2 tacked onto the end of it. So let's go through our really basic idea here and make a table of values and see what we get. Well, with negative 2 put in here, that's going to be 4, and then 4 minus 2, that's going to get me 2. Negative 1 put in there, and then minus 2 is going to get me negative 1. 0 put in there, minus 2. 0 squared is 0, minus 2, negative 2. And 1 squared minus 2 is going to get me back to negative 1. And then 2 squared minus 2, again, back to 2. So, just like in the last time, we can see symmetry going on. Negative 2 in the middle, negative 1, 2, 2. The thing that's different, though, is last time I was always seeing 0 in the center. So when I just had the a term in front, it was kind of changing. It was making it wider or slimmer. But in this case, what it looks like is happening is this point in the center is shifting. So it went down to negative 2. 0, negative 2 is a point that I have there in the middle. And if I go to the left, I have negative 1, negative 1. And then negative 2, positive 2, negative 2, positive 2. And on the right side, if I go to positive 1, I have negative 1. And if I go to positive 2, I have positive 2. So I still have that same type of symmetry going on, and I will attempt to do, almost worked. We got a curve going through now. So how does this compare to y equals x squared? Well, I'll give you like a rough estimate of what y equals x squared looks like right in here. So how does it look like it changes? Does it look like it becomes any wider or slimmer? You might think so, because it does look like it's kind of like a smaller little thing inside of this larger graph. But it's really not smaller, it's just that this one in blue, the one that we're looking at here, is shifted downward. So it's had more time to open up when it gets over into these top portions. Whereas this starts at 0, 0, the vertex here is at 0, negative 2. Okay, so we saw this when we were talking about linear functions, when it said something like 2x minus 2, that minus 2 meant the graph was shifting down. We also saw it with exponential functions, with something like 3 to the x minus 2. So something like y equals 2x minus 2, or y equals 3 raised to the x minus 2, or something like y equals x squared minus 2. These minus 2's are all kind of doing the same thing. They're all shifting the graph downward. Okay, so that rule that we have for other types of functions is still going to be true here. Okay, so that's a nice kind of easy thing to remember. Just think of it in the same way that you would think of it for exponential functions or for linear functions. It's just a vertical shift. Alright, so let's take a look at part B here and see what's happening when I have addition going on. Go back to blue. Let's fill out our table. If I put a negative 2 in there, negative 2 squared, it's going to get me 4, 4 plus 3. Negative 1 put in here, plus 3, it's going to get me 4. 0 put in here, plus 3. 1, put in here, plus 3, and 2, put in here, plus 3. Okay, so again, I'm seeing that symmetry. And if I graph it, I'm going 1, 2, 3, 0, 3 in the center. And then if I go over 1, I'm going up to 4. If I go over 2, I'm going up to 5, 6, 7. And the same type of symmetry on the other side. Ooh, I really traced those points poorly. Anyway, what are we noticing between that and the graph of something like x squared, which roughly will be something like this? Okay, again, the plus 3 this time, instead of it being a minus 2, is going to be shifting it up instead of down. Right? So you see the red is my parent function, and my blue is my new function that I'm looking at. It's been shifted upward 3 units. Every point upward 3 units. Very cool. Alright, now let's add in another factor here. In the first part, we're just looking at x squared minus 2, or x squared plus 3. Now on the other side, let's take a look at something where it says 4x squared plus 1, or negative 1/2 x squared minus 5, which we know from the previous section that these numbers in front here are essentially just going to make the graph larger or smaller in terms of how wide it is. Alright, so do me a favor and try example 2, A and B, on your own, and then we'll kind of summarize it. Alright, so pause for a second here and do that, and then I'll come back for the summary. Alright, so hopefully you've taken care of example 2, A and B, and I'll check over those in class. But in summary, compared to the equation y equals x squared, when the c value is positive, the graph shifts upward. And when the c value is negative, the graph shifts downward. Nice and easy, right? Nothing too complicated. When we look at example 3 here, it's a standardized test practice problem, and we're looking at which of the following is true when you translate the graph of y equals x squared minus 5 to the graph of y equals x squared plus 2. So I'm changing this graph into this graph. I want to move y equals x squared minus 5 to the position of y equals x squared plus 2. So really, I want a vertical shift. How much? I want to shift the graph 3 units up. So if I shift y equals x squared minus 5 3 units up, is that going to get me this high? I want to shift the graph 7 units down, shift the graph 7 units up, or shift the graph 3 units down. I'm really curious what you come out with here. So actually, I want you to kind of think about this on your own. Circle one, and I'll talk to you about it when I come around in class. And this next definition here, the zero of a function, well, we already talked about that. It's when f of x equals 0, and a 0 is a solution to a particular function. We did those when we were looking at solving certain functions that were in factored form. So it's a solution or an X-intercept. All of these things mean the same thing. 0, solution, X-intercept, all the same. So now let's look at example 4, where basically we want to take an equation and find that solution, X-intercept, or 0 of a function. I have a person, again, who went to the top of a building for whatever reason. We're not here to judge. And we're modeling, the time it takes for something to drop with this same kind of function, f of t equals negative 16t squared. And this is just representing gravity acting on that object. But I also have this little piece of information here that says that it's 64 feet high. So my starting point is 64 feet up in the air. So I also have to add 64. So this, you can see, is just like what we were talking about. It's a quadratic function that's been shifted up 64 units from when we start. Now what I want you to do is create a table of values. I'll tell you that you can use values, let's do 0, 1, and 2. After that you won't really need anything, but fill out the y values, plot it on the graph, and see what you would get for a solution, or a time, when the ball, or actually it's an egg in this case, a solution for when the egg hits the ground. Okay, I need you to interpret what's happening here in order to do that. What does X stand for? What does Y stand for? When I'm plotting these points, what is this graph modeling? What does it mean? All right, try that out, and I will see you guys in class. Good luck.